full week for most of my classes.
Yeah.
I'll still be here every day for that one.
Yeah. All right, my friends, we're gonna get started on 8.2 today. Like I said, we won't have a lot of assignment problems to deal with this in this section, but guys, we're gonna kind of keep pushing with this idea of how integrals apply to real life situations. And today we're going to kind of look at it from a science point of view where we start dealing with density and center of mass, and we want to ask ourselves, how do you use definite integrals to calculate the center of mass of an object and use densities to find masses of objects? Okay, so there's going to be a lot of formulas that come with this. I think the thing that we'll need to do is get those down in vocab and pay attention to the examples. The examples are going to be a little tricky today, but I think you guys are on top of stuff pretty well to understand what's going on. So the goals for the day, we're going to use density formulas with integrals to find what here first, kids? Find mass. And then we're going to find the center of mass using integrals. And I'll show you there's a couple of formulas for this. Center of mass using integrals, there's kind of two formulas dependent upon what information they give to you. Okay, I put one down in here, but we'll be adding another one to that today in vocab. So let's get started, guys. You've always known that density is the amount of mass per what? Unit of volume. So you've always kind of like said density is equal to mass divided by what? Okay, now here's the deal. One of the goals for us today is to use densities to help us find, what's it say up there in the goals? Use density to find mass up there, okay? Guys, when I look at that formula where density is equal to mass divided by volume, is mass all alone up there? It isn't. Okay, so my question to you guys would be, how would you rewrite that formula so that you could get mass all alone? Or if I said mass had to equal something, what would you say there, given that information up there?
Density times volume.
Density times volume. Okay, so I think the one thing that's going to be crucial today is understanding the manipulation of the formula to make that fit what we're trying to solve for today. And when we start looking at finding masses today, there's going to be a situation that from this formula we can derive that the mass then would equal a density times a what? A volume. Okay. And there's going to be certain other types of units that we deal with when we look at densities. Density isn't going to be all strictly related to volume today in terms of some of the problems that we see, but really want you to make sure you understand that we can manipulate formulas to find what we want here. Okay, so we need to know that. Another formula for stuff today is what, well, first of all, what is center of mass? Maybe definition-wise. What's it kind of say right here? Okay, a lot of the center of masses that we're going to look at today are going to be relative to two-dimensional figures or placement on an x-axis, but it's really kind of a balancing point for an object where I could pick a point underneath it and say, all right, here's the point, center of mass. If I can put my finger on that point, then that figure should do what? Balance, okay? It's kind of like saying this. If I have, okay, let's just pretend this. Here's a beam. If I put 10 pounds over here and 10 pounds over here, both at the very ends, where do you think the center of mass would be for this? Right in the middle, okay? But what if I put 20 pounds over here and 10 pounds over here? Where's the center of mass going to move to now? Closer to the heavier part to balance that. You all agree with that? And I'm guessing you've probably talked about, have you guys talked about where a fulcrum and mechanical advantage would lie in science classes before at all? Don't remember? Okay. So we'll talk about that, but the idea is you've got to pick a point where you can balance it. And if the mass is heavier on one side than it is on another, then the center of mass is going to move towards the heavier side. And we'll talk about what that looks like in terms of points of masses. We'll also talk about it in terms of a center of mass relative to a whole area today. But the first formula I've given you for the center of mass of a system is going to be, you might want to underline this, it's for point masses. Okay, it's kind of like saying I might put, I don't know, I might put 10 pounds here at point 1, 6 pounds here at point 10, and 18 pounds here at point 25. We're going to talk about point masses. We're going to talk about where is that located, okay? This formula we'll talk about here in a little bit, but do you see this little notation right down here where it says X with a bar on it? That's just telling you the X value per center of mass. So this X bar right here, that just means center of mass. Where is that located? So it's really the location center of mass. All right? And what this really says, it's a summation of all your masses for each individual point, at each individual point. That product of the mass times a point all over the sum of all the masses. And we'll look at an example that deals with that here in a little bit. Okay? An alternative formula for this that we're going to get into is this. And I'm gonna put another formula for this. You might want to write this down. It's going to be the definite integral from A to B. And then another definite integral from A to B down here. I need to make some room. Move that up a little bit. There we go. Okay, the first part is going to be x times whatever function you're dealing with, f of x dx. And then down here you're just going to have f of x dx. And I'll show you how this works here. It's going to be very different than point masses. That's going to be a center of mass for, say, maybe some object. And we'll look at some examples that deal with that today. But understand this. The top formula is going to be a formula, and I'm pretty sure it looks like a foreign language to you right now at this point. It'll make sense when we look at some examples. This formula is only relative for what, kids? And you'll know what that means here in a little bit. This here is going to be the one that you really want to focus on. I think that this one here is your most important formula, and we'll look at one kind of a problem that's going to involve that today, right? So let's talk right here, guys. In example 1 down here, it says, how do you find a function for mass involving what? Okay. It says the air density h meters above the Earth's surface is f of h, which is measured how, kids, for a density? The number of kilograms per what? It says find the mass of a, okay, what shape are we dealing with here? Cylindrical column of air that is 2 meters in diameter and what? 25 kilometers high with a base that's on the surface of the Earth. Okay, let's just talk about this. So we're on Earth, right? Well, I hope so, Parson. Where else would we be?
Mars.
Maybe someday, right? Maybe someday.
Give it a year or two.
You think it's going to be that quickly?
No.
No.
Will it ever happen in our lifetime?
I don't know. Guys, I'm going to try and do my best to sketch a cylinder. Let's do that. We all agree that the shape is a cylinder, right? Okay. Here's how this works. Now, kids, you guys have taken enough science classes, I believe. Come on. There we go. Okay. I'm going to draw a cylinder here quickly, as best I can. How am I doing? Pretty good? A little crooked? Is it really crooked? It is a crooked can, isn't it?
I wouldn't expect anything less from a Chevy.
That's what I'm talking about right there.
I was just going to say, all the news is politicians, so I try to draw a politician up here. All right? That's a pretty good joke, wasn't it?
Yeah.
I'm doing the best I can, you guys.
You're doing great.
Trying to get rid of me. Why is that line red? There we go. How about there, kids? Pretty good cylinder, right? You get the idea, don't you? Okay, so here's the deal. We know that the air density, it starts out here, it says H what, kids? Is given by some function f of h. I don't know what it is, but what I do know is the, oops, I didn't want to do that. I do know that the unit on this for density is the number of kilograms per what?
Cubic
cubic meter. Okay, now our job is to find the mass of the cylinder. Now guys, it would be great if the density of air was always the same, but where are my Broncos fans at?
Right here.
What do they always talk about in Denver?
Mile High Stadium.
Mile High Stadium, which means people have trouble playing football there because
Can't breathe as good.
can't breathe as well. The density there is, it's less dense up there, right? So the further you move up above Earth, is the density changing or is it always staying a constant? It's changing. The higher up we go, okay, so what we gotta talk about is this, guys. We would love to know how much mass of air is in this column that we're gonna put dimensions to in a second, but we gotta understand that as we move up a certain distance, h meters here, what's happening to that density? Is it staying the same or changing? And that's why we've got to understand integrals right here. We got to understand that, well, there's going to be way more dense or way more mass of air down at the Earth's surface than there is up here at 25 kilometers. Okay, how many of you guys have flown before?
Yeah.
What do they always do to the cabin in the plane before you take off?
Pressurize.
They pressurize it because they know the density up there is much less. Okay, less pressure exerted on you, your body would explode. Okay. All right, and I believe, wasn't there a famous golfer that was on a plane and that happened, lost all pressure up there and exploded? Was it Payne Stewart?
The dude's name is
That's why
Larry.
astronauts need their
Yeah.
fancy suits.
All right, so let's talk about this. So what we kind of do is this. How do we come up with this right here? Well, here's the deal. First thing I want you to understand is we're still looking at this idea of slicing this thing up. So I'm going to take a slice of this right here. Okay, we'll color that in. Okay, now keep in mind, this slice, really thick or very, very thin? Very thin, really close to what? Okay, a height. So I'm going to go ahead and call this right here delta H. Okay, where H approaches what value for a height? 0. Okay. Now this concept's going to show up a lot more when we start attaching functions to our densities, but here's the situation, guys. It says find the mass of a what?
Cylindrical column.
Which is,
2 meters in
okay, here's the deal. I want to make sure we're okay with stuff. 2 meters wide for diameter, which would make the radius how much? Wouldn't that radius be 1 meter right there? Okay. Then it says 25, ooh, I got a problem here. Kilometers. How is our volume measured? Meters. We better turn 25 kilometers into
How many meters are in a kilometer?
25,000 meters, right? All agree with that?
Yeah.
Okay, so here's a meter stick. How many of these meter sticks do we need to go all the way up?
25,000.
25,000. We're getting pretty high in the air, aren't we?
We only need one of them. You just gotta keep using your finger every time.
Count it today. 1, 2. That's getting up there, isn't it? 25,000 of them. All right. Here's the deal, kids. We say the following. We say, okay, if I could find the volume of this one slice, and I knew the density within that one slice, then I could say, all right, the total mass would be the summation of all this. So let's just check this out here, kids. We're going to do a volume of a slice first, okay? Remember doing volumes of slices before, kids?
Yeah.
Okay? So the volume of the slice, first of all, what kind of a slice shape do we have, obviously? A cylinder, then. Basically, it's going to be a circle, but its width is going to be, or height, I should say, is going to be really close to 0. And that's kind of, that slice. I drew a bad slice there, didn't I? It's okay. It's Monday, right?
Grr, Mondays.
Okay. So the volume of a slice would be pi times your radius squared. What is your radius, kids?
1.
Okay, so pi times 1 squared times the height of that slice, which is what?
25,000 meters.
Okay, but just the slice, though. We call it what?
Delta H.
Okay. All right. That would be the volume, right? Okay. But this time we're not finding volume anymore. They ask us to find the what here, kiddos? Okay. You just got done saying, okay, density is equal to a mass divided by a volume. If I want the mass, then the mass would equal, you said density times what, kids? Okay, the only part that I have right here in this slice is the what? I only have the volume, don't I? Okay, so here's the deal. if they're asking us to find the total mass of a slice, then we need to understand, or I'm sorry, the total mass of the column, then we need to understand then what the, I'm gonna start writing things like this. What do you think this means now?
Mass.
The mass of a slice. Okay? Well, guys, we can find the mass of that one slice if I would take its density within that slice times the volume. Do we know the volume of that slice already?
Yeah.
What is it? Pi times 1 squared, delta H, right? Okay. Now, how do they define then the density? Well, it says right here, the density H meters above the Earth's surface is just simply what? F of what? Now, we're gonna start having things in here like H squared plus 2H plus 17 as a function, but they're just defining it as what?
F of H.
Okay, so the mass of a slice then has to equal the density of a slice at what? So I'm gonna write D slice. Ooh, I kinda like that. Sounds like a rapper's name. D slice. Times the volume of a slice, right? All agree with that? So help me out. The mass of the slice would equal, what did we come up with for density of a slice? F of H. And what do we have for volume of a slice?
Pi times 1 squared delta H.
So here I just call that pi delta H. Oops, not yet, parsing, not yet. Pi delta H. Now, that would just be the mass of a slice. What do we want to find here? So we want the total?
Yeah.
Okay, now think about this. We had to churn everything, and since our density was labeled in terms of cubic meters, we had to get all of our dimensions in terms of meters. So what's the total height of that slice right here, kids? So we're gonna go from ground level, which we really considered what? 0 up to 25,000 times pi, or, and then the delta H would become what, kids? Now, this will make more sense once we have a function for f of h. Did they give us an explicit function for f of h at all? No. Okay. But the deal is this, I can't just find the volume of a slice anymore and run with it. We've got to say, ooh, that's the volume, but I got to take the volume times the what here now? Density to be able to come up with the mass of a slice. And then once I have the function for mass of slice, then we can move into our total integrals. So the connection I want to make from last section, are there some similarities here?
Yeah.
Absolutely. We got to slice stuff up again, okay? The difference is our formulas just aren't right there for us once we put it into a two-dimensional coordinate plane. We've got to say, okay, this is what we know, this is where we're going, so to go ahead and come up with that formula, we might have to multiply some things together, okay? So let's just take a look at this, kids. Let's go to example 2 on the next page. Actually, can I skip ahead to example 3, guys? Let's do that right there. It says example 3. Example 3 is related to example 1. Maybe make a note, okay? Maybe underline example 1 right here. These two are related, all right? So it says find the mass of that column of air in example 1 if the density of the air at height h is given by what? What was f of h equal to in this?
1.28 e to the
Total mass, right? Okay. So let's just do this. From example 1, kids. We had a total integral. Our total was equal to the, remind me what it was. Integral from 0 to 25,000 of pi f of h, is that right?
Yep.
Okay. All agree with that? So friends, what the heck am I plugging in there for your density function f of h?
1.28 e to the indefinite.
Okay, so if I want to know how many total kilograms of air are there, the total would equal the definite integral from 0 to 25,000 of pi times, okay, here we go, 1.28 e to the negative, how many zeros are there? 3 of them?
Yeah.
0.00 1 2 is that 124h? And then delta h, right, which would be dh. Okay, so once I've established that function right there, where are we running off to? Decimals, okay. So let's do that here. You guys might have to help me remember that. So it's 1.28 and 124. Okay, let me run that through you quickly. So, oops, got the wrong one. Do the do. Get my Dale call. All right. Integral 0 to what, kids?
25,000.
Pi times, what was it, 1.28 e to the negative 0.000124h. We get a value there. What is that value, kids?
30,968.427.
Okay, so let's just go nearest tenth on that. 30,968.4. How is our density measured again in that problem? Kilograms per what? Cubic meter, right? So the question really is, if I just want the mass, that would be, what unit would represent your mass there, kiddos? Just the number of kilograms there, okay? By the way, how many pounds are in a kilogram?
Like
2.2. So if you doubled that, you would have about 62,000, and then, I don't know, a tenth of that, which would be 6,200. About 68,000 pounds of air in that column. Isn't that crazy? Who said air was weightless? Agree with that? All right, so you guys have the value for me. So the total was equal, was it 30,968?
0.4. So does that factor in like gravity and stuff too? or is
Yep.
it-
Yep.
So if we were to do the same measurements in space.
I'm pretty sure, and then it's funny because we're going to get into stuff in the next few sections about gravity, and so like all of your, we're going to talk about escape velocity. You know what escape velocity is? It's like a certain speed that you have to obtain for a certain mass to escape the gravitational force of the Earth. So like how fast does a rocket need to get going so it can at least leave the Earth's atmosphere and stuff like that?
How much inertia you need or whatever.
Yeah. Who said we wouldn't be doing rocket science in here? Every time we say it's not rocket science, we might really be doing rocket science here in the next section, eh? We should start the year with that instead of ending it, right?
We still don't get an AP credit.
I know, I hear you. Okay. All right, what do you guys think about that?
Pretty sick.
It's pretty straightforward, but you've got to understand formulas. So let's kind of keep with this theme right up here, kids. Kind of keep with this theme right up here. We're going to go to example 2. This time we're going to involve not density with volume, but density with what? Area. So we've got to talk about, guys, when we start involving density with area, we've got to come up with some kind of an area formula now, all right? And the last one, we had to come up with some kind of a volume formula for that slice of that cylinder, okay? This time we're going to come up with an area. This is an extremely, I don't want to say it's difficult, but it's kind of a little bit more difficult to understand for kids. I'm going to try and do my best to make sure that this works. Well, maybe this could work. I'll do my best to draw it, okay? Let's just read this first. It says the density of oil in a circular oil slick on the surface of the ocean at a distance, somebody had an oil spill. Not good. Gas prices will be going up now again. Okay. By the way, why is it over $4 a gallon again?
It's only $3.89 Dizer right now.
Is it?
This is like five.
You guys living high life now.
This is like $5.20. Oh yeah, I saw that.
How much it cost to fill your truck there, Mr. Gibby?
$139.
Oh my gosh, That's ridiculous.
That's what it cost me.
it's insane right now.
Mm-hmm. Every week.
Yeah, it's a joke, isn't it?
Mm-hmm.
The density of an oil, or I'm sorry, the density of oil in a circular oil slick on the surface of the ocean at a distance r meters from where, kids?
From the center of.
Is given by the function. I'm just gonna cause this really gamma of r, but we'll just call it, let's just call it f of r. Is that okay, guys?
Yeah.
F of r is equal to 50 over 1 plus r kilograms per what? Now think about this. If I spill something, oil densities change a little bit. You would figure the density would be a lot higher rate of the spill, right? And then eventually it starts to spread out, okay? It says if the slick extends from r equals 0 to r equal what? 10,000 meters, find a Riemann sum approximating the total mass of the oil slick. Okay, let's just first of all talk about what's going on here. I'm gonna make a drawing down here. Okay, do your best to maybe draw a circle here. I'll try hard to draw a circle. Nailed it. Okay. All right, so let's just pretend the center of the oil slick, let's just say the oil spill, the center of the oil spill is right here. Is that okay with you guys? And that's where all the oil started spilling from. And when the oil started spilling, it started spreading out in all directions, right? Okay, making what shape of an oil spill? Okay, now, it says, write a Riemann sum approximating the total mass of the oil slick. Okay, no problem. In this case right here, our density would be defined as the total mass of the oil spilled divided by the, not this time volume, but it's a kind of a flat surface, mass over what? Going to be a mass over an area right there. Okay. So the question becomes this: how do we come up with even the mass of a slice? And I haven't even started talking about how we're going to slice that, but how do you even come up with mass given that formula? Won't mass equal a density? Density times area, right? Okay, so that's going to be important for us. Here's how this works, okay? What we end up having to do here is we get out here a certain distance r. Okay, I don't know what the radius is. I just know that there's a certain distance r out here. When we add all these up, it says, okay, I'm out here at a certain distance r. The density out here is figured based on how far away from the center you are. Here's how you slice something like this up. These are going to get sliced into little rings, so it's going to look kind of like this. I'll do my best. Oh, I screwed it up already, but hopefully it corrects it for me. Not too bad. Oh, I didn't want to do that. Human. Okay. So what we do here is we say, all right, let's look at this right here, the density out here at a certain radius r. And what we do is we slice this up into some rings like this. And these rings are going to look like the following. I can fix it. Maybe. What's going on here?
You got it.
Holy moly, guacamole. Do this on the computer. There we go. That's what I wanted to have happen. That looks about right, doesn't it, kiddos? Close. Okay, so what we do, can you guys like see all these rings that would make up this whole circle? Yeah. Okay, what we talk about right here, guys, is this. We're going to go in here and we're going to say, okay, this distance right in here that I'm talking about in that ring, we're going to call that distance delta r. Okay. Delta r. Now, that radius is really close to what value, or that delta r is really close to what value, I should say? 0. Okay, it's a really thin ring, all right? here's what we're gonna kind of do. Think of that ring as like a piece of paper. It's really, if I would cut this piece of paper and then how it's rounded out, go ahead and lay it straight. If you can imagine this ruler being rounded all the way around, looking like that, and I rolled this out after I cut it, what would it really kind of make there when I'm done? In other words, I cut this right here and then I unfold it and make it flat. Wouldn't a ring kind of become like a rectangle almost? So when I cut this right here and then unfold it, what we really get is this, kids. You really get a strip that looks kind of like this. Okay?
It's like a thin piece of paper.
It is, isn't it? Okay? I'm going to say that this is the delta R part. Whoops. Gosh, this is not working very well today, guys. Let's say that this is the, let me move this out of the way. Maybe that'll help. I'm going to move this out of the way. Maybe call this delta R. Well, Kim, that part's on. There we go. That's delta R right there, right? Okay. Now, guys, when I unfold that, isn't that top part that's really long up there really just the circumference of this all the way around? Okay, how do you find the circumference of a circle?
Radius squared times pi.
That'd be great if it was area.
I'm sure they Googled.
How about pi times diameter?
Oh, yeah.
But how many radiuses make up the diameter? Okay, so 2 times pi times the radius would be the distance around here, okay? So our job right here, guys, first of all, is to write a Riemann sum. And I'm not really going to write a Riemann sum for it. I'm going to come up really with the mass of the slice. We're going to use the mass of a slice to write an exact integral here to get it, okay? So here's how this is going to work, kids. Part A. What are we trying to find in part A? Or what are we really trying to find here again? Total what? Okay. First thing I need to do is come up with the mass of a slice. Okay. That's going to equal the, you guys told me density times what?
Density times area.
Okay, so let's go with this. The mass of the slice on this, my friends, will equal. Okay, do we know the density up there? Do they give us a density function at any distance r from the center?
Yeah.
What is that density function?
50 divided by 1 plus r.
Okay, could I find the area of this slice down here? What shape are we probably assuming the area of that slice is? A rectangle, so couldn't I just go length times width? So the area of that one slice up here, or this ring, if you will, would be 2 pi r delta r, wouldn't it? This whole length, 2 pi r times the width, delta r. Okay, so here's the deal. The mass of one slice is going to be this times this. I'm going to cheat a little bit. Are you guys okay with that? So I'm going to say our total mass, that's going to equal the integral from, okay, how many meters is our radius going out? From what to what, according to this?
0 to 10,000.
So we're going 0 to 10,000. Okay, I'm going to combine the 50 with 2 pi r. Is that okay up top? So what's 50 times 2 pi r? In other words, really, what's 50 times 2?
100.
So this is going to become 100 pi r up top, isn't it? All over what still?
1 plus r.
And then the delta r's are going to become a total or a summation, if you will, or a Riemann sum. Okay. So that's part A. That's part A right there. Then part B. Part B wants to know what's the total mass. And I'll be like, okay. What's the total mass? Well, you guys ready to find total mass?
Yeah, plug it in.
Plug it in. All right, you're gonna have to help me here. Okay, so go integral, and it was 0 to 10,000, right, guys?
Yep. That is going to be parentheses 100 pi r over 1 plus r.
Just like that.
Yep.
Okay, this looks to me to be about 3,138,699. I can't remember what the mass unit was. Was it kilograms again?
Yeah. That's all.
I'm gonna do some figuring on this. So that would be 3,138,699. That's about 3,452 tons of oil. That's a lot, isn't it?
How much was that one that went off like in Alaska, was it?
Was it the Valdez that you're talking about?
Maybe. The one that like tipped over it.
Years and years ago?
Yeah.
Well, let's just find out. The Exxon Valdez, 37,000 metric tons, okay, 41,000 cubic meters. I'd like to know the number of pounds or whatever.
How much did that affect gas when that happened?
I don't really remember. Heck, when did it even happen? 33 years ago?
I thought there was one that happened like in the 2000s though. Cause that's why like Dove had like that special lab that you can use or whatever and fish and stuff.
This is 10.8 million US gallons, so let's just say this. How many tons of oil spilled? $37,000 tons, so about 10 times more spilled there than in our problem. It's a lot.
Gosh.
Okay. All right, so you guys have that number. What is that number then for the total?
3,138,699.
Okay, so we'll call this part B 3,138,000.
699. Then I did 0.108.
Okay, 0.108. And let's see, our density up here was measured in kilograms per square meter, so this would be the number of kilograms, right? And then lastly, part C says, within what distance is half the oil slick contained? Okay, so part C is kind of a tricky problem. So let's get through part C today, and I think I'm gonna shut down there. We'll pick up center of mass stuff tomorrow, but part C, okay? Here's the deal. By fundamental theorem, kids, if you would look at f of r, some radius r minus f of 0, we want that to equal half the mass there, okay? What was our total mass there, kiddos? 3,138,699. But if I want to know half the mass, where what radius out here, where like I come out here a certain distance r and say, okay, that's where half the oil was, all right? We got to try and figure that out. So I need to know half of the total amount spilled. So somebody cut that number in half for me up there for this one. And you guys get 1,500,000 and some thousand, right?
569,349.55.
Okay, so here's the situation, kids. We're saying that there's some upper limit, not 10,000 meters out there anymore, but a certain distance r meters out from the center, which we call 0, which would equal this value. Now guys, I don't know what f of r is, okay? But I know our function, this is kind of like our function for r right here, isn't it? Or our integral to find that. F of r can only be defined by putting r in for r. So this f of r would be the 100 pi r over 1 plus r minus, okay guys, if I go into that integral function where we have 100 pi r over 1 plus r, if I throw 0 in for r, what do we get out? You're going to get 0 up top and 1 on the bottom, aren't you?
Yeah.
And what's 0 divided by 1 going to be?
0.
So f of r would still be the function that we're trying to find the definite integral for, minus 0, that's going to equal what value? Right? So isn't that kind of like saying 100 pi r over 1 plus r is equal to this mess? Hey, here we go with this. This is not too bad to do. Alright. The 0, the minus 0, that really just goes away, doesn't it?
So where's that 0 coming from?
So the 0 is like the center, right? So what we're saying is, if the oil spilled here at the very center, we would go from the center, which is really how many units from the center,
0.
to some unit r out here. We would do a definite integral from 0 to r out here that would encompass half the oil spill. Okay, so this is like saying here's your antiderivative you're looking for. You're going to plug a 0 in here for your lower limit and a certain r up here value to get to this value of 1.5 million about.
So why wouldn't it be half r? Because wouldn't r be the whole?
Oh, no, because these rings aren't staying the same size. What happens to each ring as you move out?
Oh.
They're going to get bigger, and this circumference is going to get bigger and bigger and bigger, right?
Oh.
As you move out.
Yeah.
You okay with that?
Yeah.
Okay. So here's how this is going to work. I'm going to multiply both sides by 1 minus r, but first things first, isn't that minus 0 just going to kind of go away here, kids? Like, right there. So I'm going to go ahead and distribute 1 plus r to the right side to get that out of here. So we're going to have 100 pi r, which is really 314 r. I'll call it 314.159 r. Okay, I took 100 times pi to get that right there. That's still this part right here. I'm going to take this 1 plus r times this over here to get that out of here. So watch what this does. What's the 1 times this mess going to be? Same thing, right? Okay, which would be oh, I've got a problem here, guys. We got to find an antiderivative. Yeah. I don't really want to do that way. Here's what I'm going to do, guys. I'm going to change limits on this. You guys okay with this? Let's maybe look at it this way. What value are we trying to get to? 1 million.
569,000.
Okay, let's just go 5,000, because that'd be half, right? 'Cause that's 1,568,000, right? Is that close?
Very.
So we're going to have to go higher, aren't we? Let's try 5,100. Is that too high?
Yep.
How about 5,050? Is that okay? What was the number again? 15. I want to write it down again. 1569. What am I at here? 1583. So I got to go below 5,000, don't I? I'm at 1568, so we're getting close. Let's try 5010. That's a little high, isn't it? 5,005. That's getting close. What was the?
349.55.
There's 5,004. Is that getting pretty close? One, 5, 6, 9. What were the last three numbers before the decimal?
349.
How about that?
That's pretty harmless.
5,003.912. I'll come back with a definite integral with an anti to look at that. But half your oil slick is contained in the first 5,003.912 meters. Now the thing you need to understand is this, that density, what was the density function in that? 50 over what?
1 plus r.
Okay, as the radius gets bigger, in other words, r gets bigger and bigger, like 1 plus r getting larger values. 50 divided by 1 plus r as r gets bigger, is that getting bigger value or smaller value? So 50 divided by a bigger number each time, what's happening to your density? It's coming down. So the density on the outside of the slick is much less than the density near the center of the slick, okay? Trying to think, see if there's an easier way to do that. Okay, so guys, is everything just relative to a shape anymore, or do we have to do something to the shape in terms of densities to come up with a function that we're trying to find a total integral for? Don't we have to use some formulas before I can write that definite integral now? Yeah, that's really the twist to everything here. So we'll pick up some more of this tomorrow.